Oh, okay. Let's go ahead and get started. Today we're going to be talking about a topic I've kind of grown to love over the course of my PhD, which is model-based reinforcement learning. Um, I'll note that kind of building off what Stephen said earlier, one of the things that is very unique about this lecture is it's one of the few times, I think the only time in this entire course, I get to cite people from both of my advising lineages. So part of the stuff we're talking about today was done by Stephen's PhD advisor, and part of it was done by Drew. Um, Accordingly, I decided that for the parts that were invented by Stephen's PhD advisor, I'm going to be very formal, and for the parts that were done by Drew, I'm going to be much less formal. I just gotta, do things in the spirit of the presenters. So there's a few different things I want to talk about today. The first, I just want to maybe talk a little bit about like what is a model in model-based reinforcement learning, why is this useful, why is this important, why is this a thing we should actually care about. Next, I want to talk about like what makes something a good model, what actually is the sort of properties by which we should learn one of these things, and how do we actually want to use it, things like this. After that, I want to get into the actual kind of machine learning component of things, which is beyond that, okay, here's a desiderata of what we want the model to look like. How do we actually train a model that does these things? And then lastly, depending on how much time we have, I'll be able to answer some to many questions about how do we actually scale this idea to something we can do in practice. Let's go ahead and get started. Um, so, you know, one of the things that happens over spring break is I think you forget most of the things you learned before spring break. So I'm going to try and kind of go through things a little bit and kind of recap a few things. So we talked about Markov decision processes, MDPs, a lot. And as you remember, an MDP is some kind of tuple with like a bunch of different elements. What are some parts of an MDP? Anyone?
States.
Okay, state space. Good. I'm going to call that S. What else?
Action.
Good. Okay, the action space. Next.
Reward.
Reward. Good. The reward function. Yep.
Transition.
Transition. Excellent. You're on a roll. I'm going to call it the dynamics for today, but yeah, transition, dynamics, people call it a bunch of different things. 1 to 2 other components, depending on who you ask. Anyone? How do I know how long I get to act for in the problem? What's that called?
Horizon.
Horizon. Good. And I forgot if this was in the definition that Stephen gave you, but how do I know where I start?
Initial state.
Good. You have some sort of initial state distribution. I'm going to call this rho naught. So these are all the components of an MDP, right? And kind of in a lot of the lectures we were talking about before this, you kind of know all of these things. And sort of the rest of this class is really going to be on what happens when you don't know some part of this stuff and how do you sort of account for this fact. So the next 2 lectures are going to be specifically about when you sort of maybe don't know the dynamics in closed form. So if you guys remember, our dynamics function is going to be something that maps from a state, the state space, and the action space, to a distribution over next states. Right. So just like a counting question, if I wanted to learn this whole kind of table, let's say we're like in a tabular MDP, how many elements are in this table? So we can have S by A different kind of places where we have to have a distribution over S elements. If I take the product of those, what do I get?
S squared times A.
Yes, good. At least one person is paying attention. Right. So S squared A elements. Okay. If I want to have a policy for a tabular problem, how many elements is that?
Modest times mod A.
Yes. So exactly. So SA, right? So notice how to learn a dynamics model, I need to learn way more elements. So as a general principle, one of the main challenges in model-based reinforcement learning is going to be that learning this requires a lot of data because it just requires more elements than for a policy. So when people talk about models in model-based RL, what they really mean is just a sort of like a learned set of dynamics. So some function I can query and tell me if I take this action in this state, where I'm going to end up next. So in my head, I really think of model-based RL as basically doing RL in an MDP M prime, where M prime is basically M, but with the ground truth dynamics T swapped out for some approximate model we've learned T prime. And model-based RL is just doing RL in this model. So before we get into like the nitty-gritty of like how you actually do this and the best ways to do it and things like this, does anyone have a sense of why I would care about doing this? Like, why would I want to learn a model?
Test time planning probably.
Good. So one thing I'd want to do is, okay, let's say I'm at some state in my MDP and I want to figure out what to do next. I can basically simulate a bunch of counterfactuals of had I done this, had I done this, had I done this, where would I have ended up? And I can figure out what's the best of these options. Good. So test time planning is a very old idea. It used to be called model predictive control. Or MPC for short. I'm not going to talk too much about the details of MPC today. That will be kind of 2 lectures down the line. But one thing you can use this for is that sort of like in-the-loop planning kind of stuff. Good. Any other reasons why? Yep.
Maybe rolling out either simulation or getting data useful for the learning the policy is expensive. So you want a representation that's easier to query.
Yeah, definitely. So I think it's either expensive or it's unsafe. There's lots of problems where I don't, I don't want my robot just like banging around the house to figure out how to open a cabinet, right? Like not a good thing to do. So having a model where I can try things out, see what happens, is like a kind of a useful thing for a bunch of different problems. So I think a lot of things where you have sort of like, let's say like safety critical systems, or sort of just like systems where things are expensive to sort of do real world interaction. Think about things like healthcare like this. Models are really useful for all of these sorts of problems. So yeah, overall I would say the reason we really care about model-based reinforcement learning is oftentimes it's cheaper to just do interaction in the model than interaction in the real world. And there's certain problems for which this is an important thing to do. Cool. So hopefully that all makes sense. Let's dig a little bit more into the details now if there's no high-level questions. Also, as a general principle, please just interrupt me if you have a question. So I think the natural follow-up question to what I just talked about was like, what makes something a good model, right? I don't think there's like a particularly universal answer to this question. I think it's fairly subtle, actually. There's one particular answer I'm going to talk about for most of the rest of this lecture, just because it's the one that's kind of had the most theoretical study. But I'm sort of curious if anyone has an idea on top of their head. What would make something a good model?
The one that is close to the ground truth.
Good. So something that, yeah, if I gave you a model that was perfect and was exactly what I saw in the real world, that'd be perfect, right? That'd be wonderful. The hard thing, though, is for any learning problem, right, I can't guarantee you perfection, right? Like, there's some sense in which I'm going to make errors, I have to deal with these errors. So do you have a sense of, like, what properties, if I had condition on having to make errors, I would like to have?
Bound on the error?
Bound on the error. Bound on what error?
Versus the ground truth. So I guess there's a state distribution prediction, or maybe even the KL divergence of ground truth in state.
Good. So one thing we could care about is how accurate the model is in terms of predicting next states, right? So there's some ground truth distribution of like some state to action gives you some distribution over next states. I want to make sure I match that distribution well. Yes, good. Any other answers?
Learn efficiently.
Yes, we want something that we can actually, not have to spend a crazy amount of time actually like interacting with the world to learn this model, because then it's like, why did we go through all this effort in the first place, right? Good. Anything else?
Deterministic,
Deterministic?
in the sense that it should always reliably give like the same output and like have high confidence in that output and like not have a uniform distribution over the labels it's doing.
Yeah, right. So I think it depends on the real system, right? Like the real system is very stochastic, and you could end up in a bunch of different states. You probably want a model that's stochastic, right? But I think that like for certain contexts, right, you don't want a bunch of randomness in your overall process, right? For like something like self-driving, you generally don't want to have randomized algorithms when you're like actually driving on the road. Good. Any others? Yeah.
You want to be able to query it efficiently as well as learn it efficiently.
Yep. You want to be able to actually, if we remember the access models Drew talked about, right? One of them was this generative model access, right? When I learn this model, I have generative model access, right? Because I can just query the model I've learned, right? So we want to make sure that actually sampling from this model is not some sort of crazy process that is very challenging. So I think the sort of reasonably subtle answer that a lot of people who are much smarter than myself have spent a bunch of time thinking about is the following. That really a good model, good here in quotes, is one that allows us to accurately evaluate the performance of a policy. The reason this is a bit subtle and a bit distinct from just having overall accuracy in terms of your model, right, is that like clearly if my model is perfect everywhere, I can just evaluate my policy by doing rollouts in it and I'm fine. But that might be asking for too much, right? Like let's say basically no policy in your policy class really goes to some part of the state space, right? Do I really need to be accurate there to do policy evaluation well? No, right? So essentially, if we're doing learning inside a model, the thing we want is that if a policy looks good in the model, it does well in the real world. We essentially want to guarantee that any policy that does well in simulation does well in real. That's the whole game we kind of have here. And that sort of really boils down to a model being able to accurately evaluate a policy. So there's sort of a kind of a canonical result here on how you actually sort of judge the quality of a model in terms of how well it's able to evaluate policies. This is called the simulation lemma. The right citation here, I think, is like Kearns and Singh, like 02, I think. I think so.
Okay.
Am I wrong? I think it's 02.
Maybe the first version is, this is journal version, I don't know.
Yeah, I don't know. Do you have any interesting things to say about Kearns while I'm writing out the lemma?
He played racquetball, squash.
Michael was Stephen's PhD advisor. So I'm going to state a simpler version of the simulation lemma than people usually do, just because I think the more complicated versions essentially aren't particularly useful for what I want to talk about today, but you can state this in more generality. So the simulation lemma basically looks like this. I say if for all states and actions, the following condition holds true, that if I sum across states I could end up in, S prime, and I look at the total variation distance between my learned model and the ground truth, S prime conditioned on S A, and this is less than epsilon. And if you haven't seen this before, this is usually called total variation. Then I have the guarantee that if I evaluate any policy pi in my model, and I look at the performance difference between reality and simulation, that is bounded by the quantity h times h minus 1 over 2 times epsilon for all pi. So what this says is basically that if everywhere I could end up, I have a bound on the sort of inaccuracy in terms of the next state distribution my model predicts, then I have a guarantee that no matter what policy I use, my error in terms of how inaccurate my estimation of the value of a policy is scales linearly in the total variation bound and quadratically in the horizon. So essentially what you can do is try to have this epsilon be a small enough number that you kind of have a reasonable belief that your policy is actually good if it looks good in the model. You can, under certain assumptions, you can get rid of this h squared. It requires a lot more technical machinery than I want to get into today, but if anyone's curious, you can ask me afterwards.
What's the assumption?
You essentially need to do like a fancier second order analysis. Yeah. So it's like a thing that I think why don't you figure this out like a year or two ago? So it's actually much harder than you might think. Okay, so before I get into the actual proof of the lemma, does anyone have any questions about the actual lemma? Good. Okay. So I'm going to do a proof by backwards induction. This is a proof cobbled together from like 3 separate people's lecture notes, all of which were not entirely correct, and I'm not going to say who those people were. So I'm essentially going to have a claim, and I'm going to like say this holds in for all t and kind of do it backwards in time to say the overall claim is true. So the claim I'm going to try and prove is the following: that if I look at the value of the policy at time t, starting from any state s, actually I'm going to do little h actually, in the model M, minus the value at step h of pi from s at state m prime is less than or equal to big H, the horizon, minus little h, the current time step, times epsilon, plus essentially the value error at the last step. So it's going to be v pi h plus 1 s m minus v pi h plus 1 s m prime. Also, is somebody scribing today? I should have asked that earlier. Cool. Good luck. Yeah.
Feel free to stop him if like the spelling doesn't make sense.
Yeah, the spelling doesn't make sense, or it's fairly frequent at this point for me to have a meeting with my advisors where they have no comments on the actual technical content, but they just tell me my handwriting's messy. So do let me know if just parts of it aren't like literally legible. Okay, so this is the claim we're going to try to prove. Maybe before we do that though, is it clear to people why, if this claim is true, I have I would be bounding the performance difference, right? Because essentially, if I'm saying this is true for all states, if I had an expectation over the initial states, which is what we did for like the J function, it must be true, right? Like if something holds pointwise, it must hold in expectation. So let's do the base case first. which is going to be little h equals big H. Then the left-hand side of this is 0 because we're kind of at the last step, right? And the right-hand side of this, that's going to be 0 because there's no reward in the future. And big H minus big H is 0. So we're going to have 0 is less than or equal to 0 is equal to the right-hand side. This is true for the base case. Now let's go through the inductive step. So I'm going to go through this in somewhat great detail, just because I think that there's some useful tools in here that either might show up later on homework or just are generally useful things to know in the analysis of reinforcement learning. So let's say we write our VT pi Sm minus VT pi Sm prime. We can basically expand this out in terms of the current step plus the next step, right? That's just what the Bellman equations tell us. So we can write this as being equal to the expectation over actions drawn from the policy at state S, the next state sampled from our ground truth dynamics of like R of SA plus VT H plus 1 pi S prime M. And then what we can do is subtract out the thing where we, instead of sampling the next state from our real world, we sample it from this approximate dynamics model, T prime. And the expectation is going to be of the same RSA plus V H plus 1 pi S prime M prime. So I'm going to probably forget a prime somewhere when I'm doing this, so I'm going to, maybe mostly for my own benefit, I'm going to try and circle all the times I'm going to be using the model and not the real world. So that's happening here, and that's happening here.
And T and H, small T and H are the same thing.
Is there a small t somewhere?
On the left,
Oh yeah, you're right. That should be an H. Thank you. I guess this is not the vibey part of the lecture, but okay, right. So I'm just writing things out that way. Then what I'm going to do is I'm going to basically first note that the expectation over the reward function doesn't depend on the next state I end up in, right? So the expectation of RSA in both of these two is the same. So that term cancels. And then what I'm going to do is I'm just going to, for simplicity here, I'm going to upper bound the expectation over action sampled from the policy, which is the max over actions, right? I can always upper bound an expectation with the max over things I could have chosen. So this is going to be less than or equal to the max over A of the, I'm now going to write the expectation out a bit more explicitly, sum over S prime, T of S prime conditioned on S A, V H plus 1 pi S prime M minus T prime S prime S A V H T plus 1 R H plus 1 pi of S prime M prime. So that's just expanding out the expectation, writing it as the sum. So now I'm going to introduce something that we'll use repeatedly, which is the following idea. If I have some A and some B, I'm looking at the difference in their absolute value. I can do an add and subtract trick, which is, Stephen's favorite thing to do. And you get like this A minus C plus C minus B, right? And this just holds true for any C, right? I'm just adding and subtracting 0. The thing that is a little bit interesting here is that I can upper bound this by A minus C plus C minus b. And this is usually called the triangle inequality. The vast majority of proofs in tabular reinforcement learning essentially use the triangle inequality, the performance difference lemma, and Holder's inequality. So we're going to try at least give you examples of all of those in this course. So
We weren't known.
It
is fixed.
yeah, that's a good question. In general, you can state this lemma where you also learn the reward function. I'm going to assume here that I can query the reward function anywhere, or I have learned it perfectly, just because it simplifies the analysis a bit. You play linearly in your reward error otherwise. So what I'm going to do for the add and subtract trick is I'm basically going to add in a cross term, where I'm going to basically say I'm going to take the expectation under one model or the reality. I'm going to look at the value function under the other one. So I'm going to kind of have a mix of prime and non-prime terms. So what we can say is that this is going to be less than or equal to the max over A of the sum over S prime, T of S prime condition on S, A, bless you, BH plus 1, pi S prime M. That's the term we had before. Now I'm going to add in the new terms, which are going to be minus T prime of S prime condition on S, A, VH plus 1, pi of S prime M. So notice how there's a cross term here. I'm taking the expectation with respect to T prime, but I'm in the future evaluating under M. And I'm going to add in the sum over S prime here of T prime, S prime, S, A, V pi H plus 1 of S prime M. So this is the same term as I just wrote down, right? And then I'm going to subtract out the term that the last matching term. So S prime condition on S, A, V H plus 1 pi S prime M prime. Right, so this is, you can think of A as being this guy, B as being this guy, and C as being that guy. So let's maybe first think about the first term here, right? So this guy right here. So another useful fact to know is that if I have some sort of set of vectors, let's call them P and Q, and I look at their inner product, this can be upper bounded by the L1 norm of P times the L infinity norm of Q. And this is usually known as Holder's inequality. You can state this more generally. It holds for basically any pair of things like 1 infinity where the reciprocal sum to 1. But for some intuition for this, think of P as being a probability distribution and Q as being a vector. What this says is that the expected value of these two things is upper bounded by, how often something can happen versus the worst case value you could take. So if we look at this sort of expression up here, right? So the most, the maximum probability difference we could have between T and T prime is epsilon, right? Because we said that that's sort of what we assumed. And then the maximum value a value function could take in general at step h plus 1, right, is going to be big H minus little h, right? Because that's the amount of time I still have left. So what we can do is we can upper bound this term by epsilon times big H minus little h. So the epsilon here is the L infinity kind of total variation looking thing, and sorry, the L1 total variation looking thing, and the big H minus little h is the L infinity maximum bound on the value function. Does that make sense? Any questions on that? Good. Then I think we can sort of complete the proof then, or get closer to completing the proof by just noting that, sort of by assumption, this term right here is bounded by the last step, right? Because I'm just taking an expectation over the same thing, and as long as I bound that these two are similar, no matter what distribution I took an expectation over, those two must be similar. So this ends up just being bounded by the last step. And because we proved this for the base case already, I kind of have this recurrence going. So maybe just to sort of like complete the proof, right? We can state that j pi m minus j pi m prime is going to be less than or equal to the sum from little h to big H of big H minus little h times epsilon, which we know is going to be h times h minus 1 over 2 times epsilon. And if you haven't seen this before, think of this as just basically looking at the area of a triangle. But yeah, so once we prove the recurrence, this sort of falls out naturally. So yeah, I would say overall, the kind of key steps of this proof to keep in mind for the future are, 1, expanding things in terms of just the things that can happen in the future. 2, applying the triangle inequality with the sort of add and subtract trick. 3, applying Holder's inequality. A lot of the kind of proofs of a lot of different of the classical results in reinforcement learning are essentially just rearranging this set of tricks in different ways. But maybe the moral of the story, the thing to keep in your head, right, is as long as we can guarantee globally that we have a well-predictive model, this then guarantees that policy evaluation in this model must be somewhat accurate. Okay, questions? Yeah.
Is there a version where you have a tighter bound that's catered to like d pi, like induced distribution by pi or something?
Yes, 100%. So there's a step here, right, where I essentially take like this max over actions, and this thing where I sort of say for all s I could be in, I have this bound. You can go through this entire set of steps again without either of those two assumptions and keeping the expectations over state distribution and the action distribution you would have from a policy, and all the steps will still go through there. So the general version simulation that people will sometimes state basically replaces the for all with an expectation over some distribution. And the same set of steps will go through.
Do you save a factor of h?
When you do that, no. You still have the h squared there. But you do, I'm noting here that I'm making a strong assumption of for all states it's true. You can state it on any state distribution as well. Other questions?
Is there a version for discounted MDP cases as well?
Yes. That may now become a homework question. Yeah, so basically for the discounted MDP, the proof looks very similar. Essentially what you do is when you have this sort of inductive step here, right, you just form recurrence relation and solve it, and that gives you the thing, versus a sort of sum over the sum step I did here at the end. Other questions? Cool. All right. The simulation lemma ends up being really, really important for a bunch of different kind of things that kind of come down the line. Just good thing to keep in the back of your head. That basically that if I have a model that's accurate, potentially even under some state distribution, I can use that to get guarantees as for how good policy evaluation is in the model, right? So, okay. We have now given a desiderata for what we want our models to do. We want them to have like bounds for something that looks like this. How do we actually fit a model that does this? So kind of maybe like what Steven was sort of intuiting, having a globally accurate model is very, very hard, right? Having a model that no matter where you end up tells you exactly what would happen if you had done things is a lot to ask for. So I think you might ask for something a bit weaker, So the first pass version of this that I think seems kind of reasonable is that we want a model that's accurate on the current policies state distribution. Right? Because this means that, at least for the policy I have right now, my evaluation of the performance of this policy is accurate. I think this seems like a reasonable first pass thing to ask for. Okay, so I want to fit a model that's accurate on my policy state distribution. How would I do this?
Once you fix a policy, you can just evaluate the policy and keep track of the state action and the next state and just try fitting it.
Yes. So what I could do is, okay, I have some policy, right? I could roll out that policy in the real world, see where I end up, get states and actions, get a big data set, and then fit a model via whatever algorithm I want. You can usually think of model fitting as just maximum likelihood estimation, right? Just fitting a multi-class classifier, right? Yep, definitely. So I'm going to write that out a little bit more explicitly. We're going to initialize some pi knots and some t hat knot. And then for little t equals 1 all the way to some big T. I'm using t here to refer to iterations of the algorithm, not time steps of the MDP. We're going to do the following things. So first, we're going to roll out pi t minus 1 in the real world, which I'm going to call t star, to collect some like data set. Let's call it d sub t. Then what I'm going to do is I'm going to fit t hat little t on this data set, dt. Then, okay, I fit a model that's accurate on my policy state distribution. I think the natural step would then say, okay, if I can do policy evaluation, I then want to do policy improvement. So we're going to say the third step here is that we're going to run whatever RL algorithm you want. It could be the policy gradient stuff we talked about, the active critic versions, policy iteration, whatever it is you care about. Inside t hat t to compute the next policy. And maybe a little bit more formally, I'm going to write this as pi t is going to be equal to the argmax over some policy class, pi and big pi, of the performance of our policy, pi, inside this model, mt. I'm using mt and like t like interchangeably. For reasons that will become more obvious soon enough, I'm going to refer to this as the best response. So, okay, this is a thing you could do. I'm going to bet you, a non-trivial amount of money that this would work extremely poorly. Does anyone have any intuition for why?
Basically, no exploration.
There's no exploration. Yes, that's definitely one issue, right? Like, I kind of am bumbling around in this model. Who knows if I'll ever like find a good policy? Yes, definitely. But there's an even more basic issue here.
So the policy distribution will not match in the states that the policy is not encountered yet, but we are running policy gradients, so we might explore those states as well, and we can have that error which probably compound.
Right. Like, think about all the points Drew was making in the sort of approximate policy iteration, right? I have the same problems here, right? Because I fit a model on some state distribution, and then I am trying to use it for an RL step where I'm going to query it on a bunch of things it hasn't seen before, and I'm going to end up exploiting my model, right? I really like thinking of all problems in reinforcement learning as essentially operating in tree structure dynamics. So I'm going to use that for the next few minutes. But let me give you a more kind of formal example of what we just talked about. So we're going to have some real world. We're going to call it M star. And I'm going to consider operating in like a binary tree looking MDP, right? So you start at the top of the tree and you basically go left or right till some depth. So you're going to start here, and you're going to go here or here, and then you can go here or here, 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 or here. And let's say in the real world, if you go left twice, you get reward 1. All other ways you could go, you get reward 0. And we're going to say we the initial policy we start off with, let's say it goes right. So it goes right, right, and gets reward 0. So we would then say, okay, we're going to collect some data. We're going to fit a model on this data, right? So we're going to have a policy or have a model that's accurate on this sort of rightward path, because that's where we saw data, right? So a bit more visually, we're going to have some M naught. I'm going to redraw the same thing here. And we know because we saw data going right, right, we're going to correctly predict that you get 0 reward when you go this way, right? But all bets are off for the rest, right? Because we haven't seen data. So what very well could happen is that I predict 0 for like the place you actually would get reward. Maybe I predict 0 here, I get it right. But then I sort of spuriously predict that if you go down this path where you go right then left, you get reward 1, right? This is perfectly a thing that could happen. Why not? And then think about doing this RL step inside this model M naught, right? I'm going to basically then pick the policy that goes right then left, because that's what's best in my model. So you can then think about having another model, M1, which I'd fit on this new policies data. And because we saw data looks like this when I'm fitting it, I am going to correctly predict here that you get reward 0 when you go here, right? Because I saw in the real world you got reward 0. But I could now predict over here that you get reward 1, right? So I didn't have data there. And I'm going to fill this in with 0 here and 1 here. Or, sorry, 0 here. And if I look at M1, the optimal policy in M1 is the policy I started off with, right? Because it wants to go right twice. So what's going to happen is I'm just going to keep oscillating between these because the policy exploits the model. Does that make sense?
So clarification, because you came from the simulation level. Here you actually need to learn the reward.
So you can think of this as being like it messes up the dynamics so that it puts you in a state. It thinks you'll end up in the state where you'll get that reward.
I mean, more like, in the simulation level, we only learn dynamics.
Right. So
Here, this is an example.
yeah, I'm knowing that you could also have this sort of thing if you only learn the dynamics, but you can think of it as the dynamics being so messed up, it thinks you magically teleport to the goal when you take the wrong sequence of actions. That's part of the reason I didn't want to get too into it, because it doesn't really, these things are mostly equivalent. So this is clearly not good. You just keep picking bad policies over and over again. This should remind you of what we talked about in the Dagger lecture, what we talked about in the approximate policy iteration lecture. It should also remind you a lot of I think this was in one of Stephen's lectures about the sort of things that make it so that follow the leader is not the right thing, right? Where you keep switching back and forth between things. So in all those situations, we essentially have the same answer for how to stabilize things. How should we do it? Yeah.
So is that because every time you collect a new data set, you basically drop the previous one?
Yes. So how would we? What could we do instead?
What if you just don't drop? And
Yeah, you could aggregate the data sets, right? We could do Dagger. Instead of doing it on DT, instead we could imagine fitting it on basically, let's say it's the union of all the data sets we've seen up till this time. Right? And really you can think of this as any no regret algorithm rather than just data set aggregation, right? Because the thing we really care about here is stability and not having this sort of oscillating behavior where your policy keeps exploiting your model, right? And while this is not exactly a zero-sum game, you can't write it that way, I think. I just want to note the similarity to some of the game theoretic things we were talking about earlier, right? Where we're essentially doing now no regret procedure over models and a best response over policies. A sort of theme you will see for the rest of the course is essentially that a really wide set of problems in kind of interactive learning really boil down to something that looks like a game or running some sort of no regret and best response players against each other to get performance guarantees. Okay, so let's think about what the no regret model would look like. So it's gonna, let's call it M no regret. And it's gonna, also be a guy that looks like this. And we know that because it saw data that went here and went here, we're going to be correct that we get 0 here and here, right? But we still never saw any data of the optimal policy. I'm going to call it pi star pi e. That goes this way, right? So we could still be inaccurate here. So we could predict 0 here still, right? So it's important to remember that no regret doesn't mean we do well, right? It just means we don't make the same mistakes over and over again, right? And even if I just did accurately fit a model on these two policies distributions, I would be evaluating my policy correctly, right? Because I will say I'm not going to do well in the real world, and that's true. But what I want is to learn a policy that actually does well in the real world, right? So there is kind of, to Bart's point, there's an exploration problem here as well. So maybe the simplest way to try and solve this problem is, let's just say we can get some samples or some demonstrations from the optimum policy here, right? Let's call it pi e for expert policy. If I had some samples, some demonstrations, some trajectories from this policy, does anyone have any ideas how we could use that?
Fit the model on that data set or union of.
So if I fit the model on just that data, what would happen?
If the world's not deterministic, then it has no idea what to do outside of the bounds of.
Right, exactly, right? And let's say, for example, like we think of pi e here as going, left, right? And my initial policy is going right? Then even if I fit a model that's perfectly accurate on the expert data, I have no guarantees on my own policy's distribution, right? Unless the expert policy somehow covers everywhere my policy could go. So the second idea you suggested is what we actually want to do, which is we want to fit it on both. So we're going to basically fit it on, I'm going to be very sloppy with notation here, like basically a data set that's 1/2 this sort of union of data sets we've seen before, and then 1/2 the expert data. And when you kind of put this all together, this is an algorithm called agnostic system identification. The right citation here is R&B Ross and Bagnell 2012, not Rhythm and Blues. Yeah. The way I think about this is it's essentially Dagger for model-based RL, but with sort of added expert data component to help with exploration. So maybe to sort of like kind of put everything together, what I would say is that rather than just being accurate on the current policy state distribution, what we actually want is that we want to know the consequences of our actions, both good and bad. When we were just fitting the model on the learner data, the issue was essentially our model was too optimistic. At certain places, it predicted we would get too good reward. The issue is if we don't include the expert data, we could also be too pessimistic, right? You could say that if we do the right thing, we still don't get reward. So the sort of like thing you want when you fit a model is both to know that if you do the wrong thing, there will be low reward, there'll be consequences, but if you do the right thing, you will get high reward. And you need both of these simultaneously to basically prove performance guarantees. So I'm not going to go through the details of the proof of this because it's a little bit kind of in the weeds, but I thought I'd give you a very high-level summary of the analysis because I think it's interesting. What we're going to do is say we want to compete against the expert policy, pi e here. And we're going to do the following kind of expansion. I'm going to say the performance of the expert policy in the real world minus the performance of the learner in the real world. Also, I haven't checked this too carefully. All of this is correct up to sign errors. Is going to be the sum of 3 separate terms. So I'm going to do another add and subtract trick here. The first is going to be the difference between the expert policy in the real world and the expert policy in the model. So think of this essentially the error on the expert's state distribution. You can then think of the same thing for the learner. So pi m minus j pi m prime. And then if we sort of collect the terms that are left, you'll see we'll have j pi e m prime minus j pi m prime. So we have 3 separate groups of terms here, right? So you should think of this here as essentially being the inaccuracy for pi e. This is being the inaccuracy for the learner's policy, pi. And this guy here as essentially your planning error, right? Like, if I did RL in my model perfectly, this third term would have to be less than or equal to 0, right? So, assuming we do RL well in the model, the only 2 terms we have to deal with are the first and the second. And I'm not going to go through this in detail, but essentially, what you can do is you bound these with the simulation lemma. Right. Essentially, what we proved in the first proof of this lecture was how to bound terms that look like this. So, assuming I can do RL well in the model, which means the third term must be negative, and I fit a model well on the learner and the expert state distributions, all 3 of these terms must be small, which gives me an overall performance guarantee. And basically what you do is then you use an upper bound on the terms in the simulation lemma to basically derive loss functions for the no regret model fitting procedure on the hybrid data. Hybrid here meaning combination of off-policy expert data and on-policy learner data. So I want to maybe just do a plug here for the concept of hybrid, specifically hybrid reinforcement learning. That will be what our next lecture on Tuesday will be on. Be a guest lecture by Yuda Song, who I think is probably the world's best expert in this sort of stuff. The idea of hybrid reinforcement learning is rather than purely off-policy or offline reinforcement learning, where you would just look at the expert data, or online reinforcement learning, like we talked about in everything prior in this class. You use a combination of both off-policy and on-policy data. You use the off-policy data, like the expert data, to basically help with exploration, so you don't have to figure out how to go to places. And you use the on-policy data to kind of avoid things like compounding errors. Yuda will talk about a bunch of different variants of this idea, some of which don't involve models. But yeah, I think you guys should definitely come for that lecture. So I just talked a lot. I have some other more practical things I want to talk about, but does anyone have any questions about the high-level idea of this proof, anything about the simulation lemma, this sort of like thing that makes them all good? Any questions at all?
So the proof reduced to some no regret minimization,
Yep.
for the model fitting layer.
Yes, so it reduces to basically something that looks like a best response or an approximate best response over policies in the model against a no regret sequence of no regret losses for the model fitting player, where these losses depend on both the data from the learner at the last round, or all the rounds, I guess, and the expert data.
The policy player is sort of adversarial.
Yeah, it's not exactly adversarial, but like in some sense, right, the policy is exploiting the model, right? Because it's trying to push it to places it hasn't seen. So the same sort of no regret kind of dynamics are useful. Yes. Yeah.
You're choosing the expert PIE. Do you need to know that it does well on M or M prime?
So I guess we'd want an expert that does well in the real world M, because our final performance bound is, we want to compete with that policy in the real world, right? So if the policy was kind of bad in the real world, it'd be like, well, you do have a performance bound, but it's not particularly useful. Yeah, good question. Other questions? Yeah.
So you could also just run RL, like, without learning the model.
Mm-hmm.
What's the benefit of having a model on the side?
Well, oftentimes, right, you don't want to, actually do exploration in the real world, actually try things out in the real world, right? Or you want to do as little of that as possible, right? So if you have some, like, knowledge of physics, or you can kind of fit a parametric or a deep model with this sort of stuff, you can save a lot of time there. So it's really a point about sample efficiency, which is also related to things about like safety and things like that. Yeah.
Second term, the bound on that second term depend on pi.
Will it depend on pi? Yes. Basically, you can ask me about the details afterwards if you want it in more formality, but basically it looks very much like the sort of style of analysis you do for Dagger, where essentially what you do is you say that one of the policies I've picked in the whole procedure must be good, and you have a bound on sort of like that sequence of policies you've already picked, not like an arbitrary policy. I just wrote it this way because it's a bit cleaner this way.
So do you take into account that by choosing pi, that bound?
Yeah, so right, so you when you are picking M, you're choosing the model. It's fit based on the policies you've already seen before. Yeah, yes. Good question. Any other questions? Entirely possible. That's true. Yes, I on faith I will believe you. Whoever are the scribes should check everything more carefully. Any other questions? I should also give this a name. It's incredibly creative. Anyone want to guess what this is called? It's called the double simulation lemma. You'll notice as soon as I started being, one of Drew's PhD students, the algorithm names got much better. The maybe the last kind of nuance I want to note here is that I was very specific here about saying that you are always weighting the expert data by 1/2, like no matter what iteration you're at. Not like it's a vanishing fraction or as the number of iterations go on. This is because if the expert data ever kind of went to 0 in terms of the overall proportion, then we'd kind of lose these exploration benefits. You want to have this balance of online and offline things. There's also nothing specific about 1/2 and 1/2. You can do the analysis for any pair of numbers that sum to 1. Cool. Okay. So now let's be a bit more let's talk about how we actually scale this idea to something you would want to actually do in practice. So I'm going to say that the sort of key challenge that I think scaling model-based RL faces is that your states can be gigantic, right? Like think about if you're learning to, manipulate objects from like vision, or if you're learning to drive a car, right? My states, the thing I have to model, are actual images, right? Those are huge, right? So, and predicting and doing like video generation, while we have a lot of foundation models that can do this pretty well, it's still like a hard learning problem, generally speaking. So I'm going to say that the sort of like the key challenge here is going to be that modeling pixels is hard. Even I'm trying to know if this is true. Like even if you think of like technically something like Atari or like a video game as technically a tabular problem because you could enumerate every possible set of pixels you could see, it's a very large state space. It's still very, very hard to model that accurately. And the sort of idea that I think a lot of people have converged on is that we are going to instead do things in some sort of latent space. And the idea we're going to look at is going to basically look like something like a sequential variational autoencoder, a sequential VAE, and this is usually called Dreamer. By Dan and Jar Hafner and some folks from, U Toronto, I guess. So this is the sort of architecture they have. I'm going to kind of walk through some of the details of this now. But do folks know what a VAE is? Can anyone tell me what a VAE is?
Variational autoencoder.
Yes, but like what does it like? What are the parts of VAE? What does it do?
It's usually trained to reconstruct the input in a smaller space, smaller state space, I guess.
Good. So we are going to encode the inputs into some sort of latent space, and we're going to decode them. I'm going to say that, okay, I want a pair of an encoder and a decoder so that I can reconstruct the observation, the image, even from this like lower dimensional latent space. So it's really just compressing things in some sense. So this is very similar to what we're going to have here for the Dreamer architecture. So you can really think of these sort of images, these X's, as being kind of observations. If you remember Drew's lecture on POM-DPs, you can really think of all of this as operating in the POM-DP setting more generally. You can think of some sort of low-dimensional latent state as being kind of like the states Drew was talking about, and I'm going to call these latent states. And then you can also think of there being some sort of recurrent state. If you were in a fully observable problem, you wouldn't need any sort of recurrence, but if you're in this sort of like partially observed thing, you want to have some memory of what happened before this current time step. So recurrent states are these H's here. And the thing we've been talking about, this dynamics model we're learning, is really going to be this sort of really a sequence model that basically takes a look at the past recurrent state and the current latent state and tries to predict the next recurrent state. So I'm going to write this out a little bit more explicitly now. We're going to have some encoder. It's going to give us latent ZT, sampled from some distribution, Q, conditioned on the current observation, XT, and the last state, HT. This HT is what makes this a sequential thing. Normally a VAE, I would just condition on the observation. Then, naturally, we're going to have a decoder, which is going to be something that looks like give us a reconstructed image, which is going to look at basically the latent state and the hidden state. So you should really think of these as basically being literally a VAE with a recurrent component added in as an input as well. The sort of dynamics model stuff we've been talking about for the whole lecture, that really is the sort of sequence model component of this whole thing. And for that, we're going to have some HT, which is going to be a function of the last hidden state or the last recurrent state, this encoded observation, ZT minus 1, and the actual action the learner took, AT minus 1. And then we're going to have a dynamics predictor. I guess it's more like the sequence model and the dynamics predictor, what we've been talking about. Where the dynamics predictor is basically going to say, okay, it's going to quote unquote imagine what would happen, conditioned on my kind of encoded image and actions my learner actually predicted. I know you don't see the dependence on action here directly, but it kind of filters in through the sequence model part. So this is a particular architecture for what people will sometimes call a world model. You should really think of a world model as really just a dynamics model, but done in something like image space. So you can actually like scale these sort of ideas up. The actual like policy learning thing, I'm not going into the details of how we do this for Dreamer, but you should think of it as vaguely being the sort of actor-critic style thing Stephen talked about earlier. There's some nuances that matter. You can ask me afterwards if you're curious. Maybe the question I think is kind of interesting about this would be the following. Why do I need a decoder here? Like, what is the value of the decoder? Let's say, for example, my policy pi acts purely on the latent state and the hidden state. So it doesn't actually look at the observation directly ever. Why do I still need a decoder?
Otherwise, the state can be just collapsed to 0.
Exactly, right? So otherwise, the easiest thing for me to predict would be a constant, right? I could just say my encoding is just a constant like 5. And then I could drive all these losses to 0. The reason you need a decoder is you want to ground it in reality. You need to have something such that it can't just collapse to something. And this gives you a good representation for actually, doing policy learning inside this model. A hard question, in the sense that it's still an open research question, I think is like, what is the, if not a decoder, because decoders can be kind of annoying, are there sort of other things you want to do here? I'm not going to get too much into the details of this. You can ask me again afterwards if you're curious. But imagine I was learning to drive, and my decoder spent a bunch of capacity learning how to model the leaves blowing in the wind, right? This does not have any influence on my actual driving. It's also something that, unless you drive extremely poorly, you cannot influence yourself, right? So it seems kind of unnecessary for us to actually be able to reconstruct the whole image, for us to have a good latent state for doing planning. So there's a lot of questions essentially about like, can I find like a minimal sufficient representation for doing reinforcement learning inside a model that I think are deep and interesting. The sort of, the one that I'm the biggest fan of basically says that we are going to get rid of the decoder. And what we're going to do is basically, from the encodings at 2 different steps, try to predict like the action that transitioned you between them. It's sometimes called an inverse dynamics model. And you can prove that this essentially will make it so that you will filter out the extraneous information. Because if I can't affect like the wind like moving in the trees, there's no reason for me to encode that because it would be not useful for me to predict the action that it should be between things. To show that you don't throw out all the information you want and learn something kind of useless, you need stronger assumptions. But there's a really nice paper on this called Agent Controllable State from like John Langford and the rest of the MSR folks. John was also, we talked about his work earlier, and we talked about conservative policy iteration and stuff like that. But this is what he's up to these days. Maybe to sort of like close out the lecture, I thought I'd show you guys an example of what world models can do today. There's this robotics company called 1X that does a lot of cool stuff with world models these days. In fact, some of my former students work there now. But, you know, we're able to get like really cool kind of interesting behavior and things, right? Like all of this is entirely simulated. You train this on a bunch of data. What I'm able to do is say, okay, if I tell my robot to move this way, this is a sort of visual observation it will actually see. And the details matter here, but they're doing something fairly similar to the sort of dreamer style architecture we just talked about. And if you look at the way you fit these models, right, it matters a lot. You have this sort of balance of fitting things on off-policy data and on-policy data. The whole thing kind of works. I think that they're currently at the stage of just doing evaluation, not policy improvement in the model, but who knows what comes next. I can show you a bunch more pretty GIFs. You can like, you know, move curtains. You can open drawers. You can, you know, not exactly pull out a chair. You can do a bunch of other things like this. So I bring this up to say that like model-based reinforcement learning, I think, is currently on the rise as something that is scaling better and better to a lot of different problems. And right, you can imagine that if you have robots in the home, you don't want them just banging around your house to figure out how to do things. Doing things in simulation would be much safer and easier.
These are simulation?
Yep, these are all simulated.
So these pictures are fake?
Yes. Yeah, it's cool stuff. I think they also do some of the failure cases at the ending. Let me see. Yeah, so there's certain things where like, because you're just learning this all from data, sometimes certain useful inductive biases aren't there. So for example, I think like here, like the object just disappears from the hand, even though that would never happen in the real world. You could think about other things where like, it will like, you know, certain laws of physics, it won't be able to actually respect correctly. I think my favorite one they showed was they tried doing things in a mirror, and it does the reflection incorrectly. Right, because that's a kind of hard thing to learn directly from data, because you don't see a huge amount of mirrors, and you got to learn that perfectly. So I bring this up to say that like there's still, this stuff is very cool. Seems like it works actually decently well in practice, but there are still open problems and interesting things to fix about how do I sort of incorporate good real-world structure into these models, and yeah, and sort of how they kind of fit into the overall kind of pipeline. So we're at time, but I would say the things I would take away from this lecture are really that a good model is one that allows us to basically know what will happen if we do the right thing or the wrong thing. To get such a model, we need to fit this model on a mixture of data from what we've done and data what like of an expert has done in a way that looks very similar to Dagger. You can scale this up via using techniques that look kind of like a VAE. And when you do this, you're able to get kind of things that look like this or even better in certain circumstances. Yeah, I think that's about it. Thank you.